Okay, perfect. So this is a good technique to know about. This technique, in addition to the previous paper that the same authors wrote, is going to give you normalization-free neural networks. But why do you want to get rid of batch normalization? I remember that one of you mentioned that computing those statistics, the mean and variance, is going to slow down your algorithm. And that's correct, especially when your mini batch size is huge. And now you're doing large scale image processing. It means that you're having bigger batches or bigger mini batch size. So you want to get rid of batch normalization because of that. We know that there is some discrepancy between the way that you train a neural network that is batch normalized and the way that you're going to call it in production when you test it, when you use it during inference time. There are some discrepancies there. So it would be good to get rid of those discrepancies. Whenever you look at other examples in your data set and your model is actually doing it through the mini batch statistics, you are breaking the independence assumption in your data, because we were working under the assumption that image 1 is independent from image 2. The label for image 1 is independent from label for image 2. So you're breaking that independence assumption when you use batch normalization. Why is this problematic? If you go back to large mini batch stochastic gradient descent, we saw some problems. We need to take good care of batch normalization. We needed to be careful when we were scaling to multiple GPU doing data parallelism. This was a sort of bugs. This can lead to bugs in your code, and then you don't know where is that bug coming from. So you have to be really careful with how you do batch normalization. That's another reason you want to get rid of batch normalization. Another one is sometimes you're taking derivatives of your neural network with respect to the input, and then you are messing with the gradients. Sometimes you want to do that. Sometimes your neural network is going to cheat. It's going to look at the examples that are similar to the example that you're working with, and then make a decision based on them. And this is cheating. And the idea is that the information is leaking from some other data to this particular data that you're looking at. And then you're also sensitive to the batch size. If your batch size is small for some reason, maybe you're working with videos, and then you cannot fit more than one example per your GPU. And your mini batch statistics are gonna be crazy, and you're gonna have a high variance. So for those reasons, you want to come up with a normalizer-free residual neural network. The idea is that you're gonna modify your residual block. You're gonna put a parameter alpha, you're gonna introduce another parameter beta L per each layer. And basically, whenever you have an input to your residual block, you first divide it by beta, you push it through 1 by 1, 3 by 3, 3 by 3, 1 by 1 convolutions. You multiply it by alpha, there are some nonlinearities here, ReLU, and then you're gonna add back HL to it. HL is the input to the ELF layer. What is the catch here? You have a function, FL, which is this branch, and you want to control its variance. You want the variance of the input to this function to be equal to the variance of the output to this function. This is your objective, especially when you're initializing your neural network. And then if you manage to do that, you don't need to do normalization anymore. Okay, so you can get rid of your normalization because the variance, you're controlling it from one layer to the next one. Alpha is going to give you the growth rate of the activities. And basically, it's going to be the variance of HL plus 1 is going to end up being variance of HL times 1 plus alpha squared, because you're controlling the variance of your F. It's going to have the same variance as the input HL. So it's going to be variance of HL times 1 plus alpha squared. And you're sort of making the assumption that this branch is independent from the previous branch, which is an approximation. Okay, so we are being a little bit hand-wavy here. How do you control the variance of your input, HL? You divide it by the variance of HL. So that's your beta, that's your alpha. Alpha is a hyperparameter that you choose. Beta is always that, especially when you're initializing. And then to make sure that the variance of FL is equal to the variance of input, you're going to use this trick, scaled weight standardization. What is that? You subtract the mean of your weights, divide by the standard deviation of your weights. This is the mean of your weights across the J It means that you're doing a mean over the m dimension, and you're computing the variance across the j dimension, across the columns. This is very similar to weight normalization, where you're normalizing your weights. Here you're standardizing your weights. For weight normalization, you're going to take that weight divided by its norm, so that your weights always have a norm of 1. Here you're controlling the variance, because in the end of the day, your FL is a bunch of weights that you're multiplying by each other. And this is one way of controlling it. There is another catch. If everything was linear and nice, then you would just stop there. Scaled weight standardization is going to give you that. But then there are some nonlinearities in between. How do you control it? You multiply your ReLU by gamma, which you're going to find through careful math. Do you remember the type of math that we were going through when we were delving deep into neural networks, how to properly initialize them? It's the same thing here. So you're just trying to make sure this happens. And then in the end, this is going to ensure, these steps are going to ensure that F is variance preserving. And then you can get rid of normalization. And that was not enough. Making the normalizer-free ResNet is not enough. You needed this gradient creeping to actually make your neural network converge. And in the end of the day, this is one of the state-of-the-arts these days when it comes to ImageNet top-line accuracy. And it's in 2021. This is one of the state-of-the-arts. So if you want to beat a paper, you need to beat this paper in terms of accuracy and in terms of latency. How many images are you processing per second? I guess I'm gonna stop here. For those of you who have questions and want to stay and ask, I'll be around. For those of you who want to leave, we can leave. Yeah, in terms of what are the downsides of batch normalization, one of them is that you need to compute your statistics. Usually, if you're sitting on multiple GPUs, then your GPUs need to communicate with each other at some point, and that's expensive. It's going to make your neural network slow, especially when you have bigger batch sizes. That's one of the downsides. Another downside was when you have larger mini batches, you have to break your mini batch across multiple GPUs. And then whenever you're doing distributed training or data parallelism, there are some pitfalls that you need to be careful about. We went through them in another paper. This can lead to bugs. Suddenly your neural network is correct, you're doing it correct, you're training it correctly, but then you're not converging. And that's because you need to be really careful with batch normalization and how you do it across multiple GPUs. Another one is that because of batch normalization and because you're looking at your other data sets, your network might just read off the result. This you don't see it for classification, but later on when we do unsupervised learning, this is really important. So we need to get rid of batch normalization or be very careful with it to make sure that a neural network is not cheating to make its decisions. We're going to see that later on. And sometimes you want to take derivatives of your output with respect to the input. Why would you do that? Because this is going to tell you how sensitive your neural network is to small changes in your image, or where is your neural network looking at. But because of batch normalization, because it depends on other data in your data set, in your mini batch, it's going to confuse your neural network, and it's going to confuse your results, your visualizations, or trying to understand your neural network. And I can go on and on. You cannot use batch normalization for recurrent neural networks. You cannot use it for, you can use it, but it's going to give you suboptimal results. You cannot use it for something like transformers. It's giving you suboptimal results whenever you have sequential data. Okay, and there are many good things about batch normalization, actually. Without batch normalization, you wouldn't be able to train deeper and deeper neural network. And you see, to get rid of batch normalization, you need to do a lot of work. It's not trivial. So yes, Sabrina, for this, I don't want to go into details because it's going to take us a few other sessions, because the math behind it is exactly similar to the math behind initializing your neural networks properly. So you need to go through a similar math to what we were doing here. And where exactly is that the square root of 2 coming from? It's because of your activation function being ReLU. This part shouldn't be that hard for you. You can just take your input that has variance of 1, multiply it by a matrix, and then the outcome, you want it to have the same variance as your input. It means that you need to have some conditions on your weights. And these are the conditions that you need to have on your weights so that the variance doesn't change from input to output. Okay, these are not rocket science. These are not hard math, but you need to be careful. Okay. Any other questions? So yeah, that's a good one. What videos should we watch for the next session? We are going to go to small networks for the next session. So far, we were not worried about how efficient our neural networks are, but then starting next session, we are going to start worrying about that. Can you fit a neural network on a smaller device? Can you make it faster? So start with watching knowledge distillation. I will cover this, which shouldn't take that long. So you should watch deep compression, SqueezeNet, and then XNormNet. And try to watch as many of these as you can, because I'm just going to be covering only this paper, ShuffleNet v2, and model pruning. The rest of it is available online. Okay. Any other questions?